I equals 1, 2, da 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 n. So that makes the partition equal. So I'm saying a partition by equal size. And that's, when Dr. Joseph did it, did he assume that the rectangles were equal size? Probably not, because it's not a lot more mental effort to allow the rectangles to be various sizes. And that's what's typically done in an undergraduate analysis book. We allow rectangles of variable size. And I've been somewhat cagey about this x sub I star. But what I mean there is where x sub I star is an element of, well, the ith subinterval, which is x sub I minus 1, comma x sub I. Now, of course, we teach you in Calculus 1, if you pick the right endpoint of the ith subinterval, that's the right endpoint rule. If you pick the left endpoint of each ith subinterval, that's the left endpoint rule. If you pick the middle of those, you got the midpoint rule. When I prove the fundamental theorem of calculus, I pick the point in the middle, which is nice for the mean value theorem. Let's see here if I can illustrate that. So, of course, what is delta x, right? B minus A over n. Now, some things here not too bad to prove, right? Not too bad. I mean, there's an obvious question here. Now, how did Dr. Joseph say to choose the sample points? Did he tell you? You guys remember? How did he say? The x sub I star, how do you choose those? It could be anything, right? To me, that's what makes it the Riemann integral. But that begs the question, isn't this ambiguous then? How do you know that your choice of sample point doesn't change the output of the integral? But epsilon delta definition? So what you're saying is you take upper and lower sums and take and find what they squeeze to as the partition gets finer, something like that. Yeah. Hmm. Hmm. Yeah. I mean, there's some discussion of upper and lower sums in the Salas and Hilly calculus book, for example. But I mean, there's obviously a question there, right? Like, why is this not ambiguous at this level of discussion? But I mean. Let's see here. What if, let's try something. If there exists a big F, right, such that df dx equals to the given f of x, then on the closed interval, and then if we look at the ith subinterval, there exists x sub I star such that what? F prime, big F prime of x sub I star equals to what? Well, by construction, f of xi star, right? But by the mean value theorem, we can choose this x sub I star such that it's equal to f of x sub I minus x sub I minus f of x sub I minus 1. Oh, I know what's bothering you. It should be bothering me too. it's really quite offensive. What's horribly, horribly wrong in my calculation right there? Duh. Did I? Oh, look. Well, at least I didn't do it over here. Okay, good. Oh, I cannot guarantee it'll be unique. That is true. I don't care, though. So look at this. The nth partial sum, right? You've got the sum I equals 1 to n of f of x sub I upper star delta x. So using the mean value theorem, we can replace that with what? This, right? Big F of x sub I minus f of x sub I minus 1 divided by delta x. What happens with the delta x? Cancels, right? And what do we have? You said f of b minus f of a. Now, how do you know that? Yeah, so in other words, everything cancels except for that guy and that guy. But by construction, the nth term of every partition here is b, and the 0th term of every partition is a. So you're just looking at f of b minus f of a, which of course is what? That's the fundamental theorem of calculus if we pass to the limit. Okay, so I mean, like some things, I mean, this is not a bad approach. I mean, some things can be proved and they're not that hard to prove, like this, right? If you have a differentiable function. Well, yes, I mean, we also prove that if f is continuous, there exists a area function whose derivative is little f. So we don't need differentiability of f, we just need continuity of f. Then we can prove that there exists a big F which differentiates the little f. I don't need differentiability of the integrand, I just need continuity. So, okay, great. This is the typical setup, right? And we tell things to people. Like, so if you're integrating, if you've got a function, right, la 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 la, and you're going from A, to B, to C, right? One of the things we teach you early on is the integral from A to C of f of x dx is equal to what? The integral from A to B of f of x dx plus the integral from B to C of f of x dx, right? How would you prove that, though? How would you prove that? Hey, man. Still teaching at this time. That's right. Okay, coming back. It's not the first time this semester he's called me at this time. So, I mean, if you're willing to give proofs at the level of geometry, well, it's supposed to be modeling the area under a curve, right? So if I want the area from A to C, then certainly the area from A to B plus the area from B to C should match up, right, just by intuition, right? But that's not a proof if you want to get fussy. So if you want to get fussy here, and you really do accept that this is the definition, what do you have to do? The way I see it, you have to explain how you can take a partition from A to C and break it into a partition from A to B unioned with a partition from B to C and show that they match up. Now, I've done this. It's in my Calc 1 notes. But it took me the better part of a faculty meeting to write it out. I mean, it took me a long time to sort through how to actually formulate that. It's really quite awful. If you think about the details of chopping the partition too. I mean, it's not, you probably could do it. If I made it as a homework problem, you could figure it out eventually if I made it worth 100 points or something, right? I mean, it would have to be a lot. Easier. Not divide into equal intervals. Yeah, so fair enough. I mean, some of this may be an artifact of the naivete of the Riemann definition I'm working with. Fair enough. But this becomes almost trivial in the Lebesgue viewpoint. We already have this over here, and why is this true in the Lebesgue viewpoint? You can almost see it in terms of the characteristic functions and how this works out, right? Because the sum of the characteristic functions, there are those that cover E and there are those that cover F for non-zero values of phi, and they don't interact. So if you want the ones that give you the non-zero part in E, they're that. The non-zero part in F is that, but this is the same set of values. I mean, you can almost just see it if you start looking at the definition. And that's not a see it as in look at the areas and they match up kind of proof. I mean, you could formulate a careful, stupidly rigorous proof of it if you wanted to. What's that? That is true. It does come at the cost of understanding what the setup is. So, yeah. But this is, I mean, every time a student covers the Lebesgue integral, I always ask them to prove this for me using the Lebesgue formulation, and they never do it. And I think it's because they forget, because I don't think it's actually that hard. So this is something I'm always, so hopefully we'll come back to this again once we actually have the full, I mean, we just have simple functions right now, right? So at the end of it, I'm hoping, we have a couple different goals, right? One is to build the Lebesgue integral. The other is to understand how the Lebesgue integral reproduces the Riemann integral. I guess we have a third problem, which is what is the Riemann integral? Because Kang is giving me a more nuanced view of it than I'm remembering. And you guys are also giving me, I mean, what is the real, will the real Riemann integral please stand up, you know?
If you're talking about epsilon delta definition, then you're going to stumble along.
So you're saying that...
Because I was in my head center, and I think Dr. Joseph was teaching that class, and many students come to ask about it.
Yeah. Well, that's always a question, is are you allowed to use theorems, or do you have to prove everything from the definition? You know, because if you can't use theorems, then Some things get much more complicated and needlessly so. I mean, we do this in upper level math classes sometimes. We say, prove this from the definition. It's actually very bad math. Because we should say, use theorems which are appropriate to the problem to solve it, right? And then make people responsible for proving those theorems. That would be better for them. But I don't know. I mean, I can't say this with authority. There is something to be gained from working out a hard epsilon delta proof or a hard epsilon n proof for a specific example. The specific inequality battle that you do there does hone a certain skill that would be hard to hone otherwise. I don't know. I have mixed feelings. I have never taught it, so what do I know? I know nothing. I know that I'm finishing class 3 minutes early, though. Unprecedented.